Deep Learning for Implementing Self-Driving Cars, a student research grant project done by Preston Lee. So a little bit of background. Artificial intelligence has never been more prevalent than today, with it infiltrating our everyday lives in things like Amazon's Alexa, Spotify's music recommendations, or TikTok's For You page. This research goes into deep learning, which is a subfield of machine learning, which is a subfield of AI. One could consider deep learning to be a simulated brain you teach. So some of the guiding research questions. The first one is, how can we use deep learning to make a self-driving car? The second one is, how can we improve upon self-driving car algorithms? And the third one is, how can we apply the existing deep learning algorithms in the real system and refine the performance corresponding to a new environment? So this study pursues the concept of utilizing deep learning in order to create a self-driving car, understanding how other companies are working on their designs, how to make one, and what a perfect self-driving car would look like. So a little bit of a summary of deep learning. Deep learning attempts to mimic the human brain, albeit far from matching its ability, which enables systems to cluster data and make predictions with incredible accuracy. And deep learning is essentially a neural network with 3 more layers, which we will get into in a moment. These neural networks attempt to simulate the behavior of the human brain, allowing it to learn from large amounts of data. One way you could visualize deep learning is with this image of how deep learning is you learning, and the neural network is your brain. Some examples of deep learning include voice-enabled TV remotes, feature extraction from images, detecting disease, and of course, autonomous driving. So, a little bit of a summary of neural networks. Inspired by the brain, they consist of many small units called neurons, which operate as functions with inputs and outputs, with each layer building up the previous. In 3 Blue 1 Brown's example, there's a multi-layer neural network that breaks down each pixel of an image to figure out how to tell which number a handwritten number is. A neural network learns by repeatedly modifying these weights, and we won't get into these weights, but just know that that is how a neural network learns. So some of the benefits and disadvantages of autonomous driving. Some of the benefits and pros include improved safety on the road, less traffic, and easier parking, but some of the disadvantages and cons are it's heavily reliant on available energy, those who drive for a living are at risk of losing their jobs, and very risky maintenance. So some of these dilemmas, issues, and roadblocks. Some legal issues include, could the government shut down a criminal's car? And who is at fault if a driverless car crashes, manufacturer or owner? Some ethical dilemmas include the infamous trolley problem, and should the car hit the older or youngest person? And some technical roadblocks are data processing takes a lot of storage power and electricity, sensors are pricey, and handling bad weather will be difficult. So the 5 levels and 4 pillars of autonomous driving. We won't go too into detail about these, but think about level 1 to 5, with the lowest one being one thing that's automated, like cruise control, and 5 being full automation, and the levels being in between. And the 4 pillars of autonomous driving, perception, localization, planning, and control, are basically the foundation of what you should focus on in a self-driving car. So how does Tesla do it? Visual feedback is fed into the Tesla's computer via many sensors, like 8 onboard cameras, a radar sensor that constantly detects objects, which Tesla uses radar instead of LiDAR because Musk has said, even if LiDAR was free, we wouldn't put it on. Not least because LiDAR is notoriously unreliable in rainy or dusty conditions. And 12 ultrasonic sensors that create spatial awareness for the system. And you can see this ultrasonic sensors in the front and back, all the 8 cameras, and its radar sensor. And the key thing about these is the visual fields of the cameras overlap, which provide crucial redundancy of the footage. Now, how does Subaru do it? The Subaru EyeSight system contains 4 technologies, and this is not the same as Tesla's autopilot, however, because it does not enable autonomous driving, but instead is a step in the right direction. And I would say this is between level 1.5 and 2 for autonomous driving. So some types of algorithms. As you can see, there's supervised, unsupervised, and reinforcement. And essentially, supervised algorithms are like your parent teaching you how to ride a bike, while unsupervised is you figuring out on your own, while reinforcement learning or reinforcement algorithms are you guessing how to ride the bike and being given candy if you do it right. So a theoretical perfect scenario of self-driving vehicles. A self-driving car should not violate Isaac Asimov's first law of robotics. A robot may not injure a human being through inaction, or through inaction allow a human being to come for harm. Before a perfect self-driving car can exist, there needs to be a transition period or training period that will likely take many years, which is happening right now. So some of the qualities of a perfect autonomous car include it's able to react accordingly to an unpredicted scenario, like a deer on the road, and able to be hacked, and minimizes damage to the environment. While qualities of the perfect car environment include upgraded road and power grid structure and able to coexist with human drivers. Now, for training the perfect self-driving car, one way we could possibly do this is to do it through software. We could simulate realistic sensor feedback and countless scenarios because you're doing it on a computer. And instead of just giving it a bunch of images to learn from, you could train this neural network by example. Like you're playing Forza Horizon 5, driving safely, of course, and the car can learn from that. So on to the experiment. This experiment will be taking the Chatbot AI kit on a racetrack to teach it how to follow road lines and avoid obstacles. And part of this experiment is training the neural networks of the AI to allow the Chatbot to drive in realistic scenarios. So setting up the AI kit, it's very simple. You just assemble all the parts and get all that. And I would like to note there's a single camera that allows the Chatbot to see where it's going. So setting up the Chatbot software. For setting up the software, I originally wanted to use NVIDIA's Isaac Sim training software, but I was unable to install it. Instead, I had to take the manual approach and run Jupyter Notebook, which will allow me to tell the Chatbot what to do. As you can see here, this is what the Chatbot sees. So training the Chatbot. So I took 8 steps for each neural network. Step 1, I placed the Chatbot in different positions in the road. Step 2, store the varying XY variables with values with images corresponding to where we want the Chatbot to go. For example, over here, I tell it to go left. Step 3, install and set up the libraries. Step 4 is we split the set of pictures into train and test sets. Where the training set is what the Chatbot will learn from, and the test set is what we will use to verify that Chatbot has learned. Step 5 is we utilize transfer learning and regression with the ResNet 18 neural network. And by repurposing this pre-trained model, it is much simpler to adapt to new environments. And what transfer learning is we'll take all these images and we will use it on an already trained neural network. What that does is it makes it much simpler, much easier to retrain this neural network for a new thing. And regression is essentially using past inputs to predict future inputs. Step 6, we train for 50 to 90 epochs and save the best model. Step 7, we convert the images from camera format to be able to be understood by the neural network. And step 8, we manually modify the gains and biases as the Chatbot drives around the track in order to improve chances of success. So the results of this experiment. The first attempt went pretty rough. We only had 124 images and had a lot of technical issues. The second model went a little better. There was more diverse images and more epochs during training. As you can see, it was able to go around, and if the video shows it, it was able to go all the way to the edge, but then got stuck. The third model was much more consistent, where it started off a little rough at first, but then was able to go around even better. And then it got stuck under this futon. But the fourth model was successful, where it was able to go around the entire track successfully, albeit it was a bit wobbly. And this fourth model took 580 images, and I tested around the settings a little bit. And though none of the neural network attempts were perfect, this shows much potential for perfection of a neural network with enough training. So the results of this continue. Again, all we need to train a neural network to drive is lots and lots of images and time. So answering the research questions. How can we use deep learning to make a self-driving car? A growing number of companies are releasing level 2 autonomous cars, with which means we're growing at a slow but incremental rate. The key part of having a car drive itself is the system, as demonstrated by many modern companies and projects like Tesla and OpenPilot. There is much hope for the future. All we need is just a neural network that can do it. How can we improve upon existing self-driving car algorithms? There are hundreds to thousands of different algorithms with different abilities. With more time to complete this research, I would have gone more in depth on the runtime, space complexity, and how different algorithms could coexist in neural networks. Creating descent algorithms seem to be very efficient for finding better outputs. For example, think of rolling down a hill, with the bottom of the hill being the best output. And I'm not really going to go into detail about how a gradient descent works, but just think of taking all the possibilities of a neural network and mapping it on a 3D plane, and each time an epoch is ran, it'll slowly move in the right direction until completed. How can we apply the existing deep learning algorithms in the real system and refine the performance corresponding to the new environment? This is essentially the Chatbot experiment. Ideally, a system should be able to recreate its entire environment in 3D, be able to analyze it, and input new factors, kind of like a video game. Tesla is currently working on this with their approach to the autopilot program. Essentially, they take in all the data from their Tesla cars that are currently on the road and driving, and send it straight to HQ for processing in order to improve their autopilot program. Ideally, a car should be able to react to new scenarios like a human, but that is just impossible. We have to treat neural network systems in self-driving cars like teach a newborn how to drive. I use to say this because they don't know much and cannot infer from situations they have never been in. In conclusion, self-driving cars are the future. How computers felt 20 years ago today, or how computers felt 20 years ago compared to today, will be like how we work with cars now versus in 2042. Deep learning is the best way to create autonomous cars. Here are my sources. Thank you for listening, and I hope you have a good day.